The story of the building of the Canadian Pacific Railway more than a century ago is well known today, and it belongs to the heritage of our country. But now, there's a new story to be told. The story of the greatest railway construction project by CP Rail since that time. This is a story of vision and foresight, of infinite planning and of inventive design. It's a story of intricate logistics and of complex machines, of sophisticated computerization and of basic construction. It's a story of massive dimensions and of pinpoint accuracy. But beyond all these, this is a story of human skills and endeavor, of extraordinary achievement, and of huge challenges met and overcome. This is the story of the Rogers Pass project by CP Rail. Rogers Pass, British Columbia. A wilderness little changed by time. Aloof, majestic, monumental, an awesome work of nature. Yet Rogers Pass has been railway territory for more than 100 years. And throughout that time, it has tolerated the railway, but has never been completely conquered by it. Listen to Omer Lavalley, Canadian Pacific corporate historian and archivist, as he talks about the railway in Rogers Pass.
At the time of the building of the railway in 1885, Rogers Pass was a formidable obstacle. It was only by sheer drive and effort of will, as well as by daring engineering devices such as the famous loops, breathtakingly high trestles, and toe-clinging construction on unsympathetic slopes, that the builders confounded nature and pushed the railway through. But nature had her revenge. Every year in Rogers Pass, an average of 970 centimeters of snow fall, enough to bury a train 2 or 3 times over. In the winter of 85-86, a party of engineers was left at a camp in Rogers Pass, specifically for the purpose of observing the snow conditions and particularly the positions of known avalanches on the mountainsides. A major uncontrolled avalanche could really be very destructive. And on the basis of this information, in the summer of 1886, even as the first trains were running along the line, wooden snow sheds were built across the railway line at these danger points. And as you can see, they diverted the fall of the avalanches and carried the snow safely across the tracks without blocking the railway. Lest the impression be given that this was the end of the problem, in fact it wasn't. A completely different circumstance resulted in the line being abandoned in 1916. The pass was abandoned as a result not of the snow, but of the imperatives of increasing traffic. By the first decade of the 20th century, what is now CP Rail was experiencing a vast increase in traffic volume, in train size, and motive power and rolling stock had not yet begun to keep pace with it. As a result, the company decided upon a program of double tracking the whole main line from Montreal and Toronto through to Vancouver. When this planning came to the pass area, a look at the configuration of the track indicated that it was not practical to extend double track around the loops on the west side of the pass and through the pass. And so the decision was made to build a tunnel under the pass.
This was the 8-kilometer-long Connaught Tunnel built in 1916. It has served the railway very well for more than 70 years. But now, constantly increasing rail traffic and today's heavyweight 100-car trains are creating a new problem to be solved. Jim Bromley, Executive Vice President, CP Rail, knows it well.
The capacity of this line has still not been reached, but on a practical basis, we consider that we can run not more than 15 trains westbound on a sustained basis a day.
Not more than 15 trains a day. With traffic increasing and expected to continue to do so, railway capacity westbound could soon become inadequate. That's the problem. But what's the reason?
The reason we are unable to run more than 15 westward trains a day on a sustained basis at this location because of a 2.2% grade, and it's right there. Now, a 2.2% grade may not sound like very much, but when you're running trains of 13 to 14,000 tons, it requires additional locomotives to get up the grade. The cutting in and cutting out of these additional locomotives, which we refer to as pushers, takes time, delays trains, and this delay restricts your ability to 15 trains a day in a westward direction on a sustained basis. Well, the solution is fairly easy. What we have to do is reduce the grade so that the pusher operation is not required. However, to reduce the grade is very difficult.
Difficult or not, Russell Allison, President of CP Rail, knows the commitment must be made to increase railway capacity westbound.
If additional rail capacity were not put in place, the railway would suffer because we would be unable to handle all the traffic being offered. The shipper would suffer because he'd be unable to ship his increased traffic. Western Canada would suffer because development would be impeded, and this would adversely affect all of Canada. And so, having foreseen these problems, CP Rail determined to do something about it.
So the commitment was made, and it was simply this. CP Rail would increase its westbound rail capacity. And it would be done by reducing the grade from 2.2% to only 1% over 35 kilometers of one of the most formidable obstacles to rail transportation that can be found in all of Canada. The Rogers Pass project, as it is called, is the biggest undertaking by the company since the original building of the railway more than a century ago. John Fox, Vice President Engineering Special Projects of CP Rail, was the man chosen to push this huge project through. Here's how he felt about it.
To undertake a project of the size that we have undertaken in Rogers Pass, and believe me, it's a big one, I think an individual has to, you sort of have to grit your teeth and say, hey, there's a hang of a pile of work here. And so far as I personally am concerned, I have to tell myself that I got to have some real good people. And I got to go out and I got to be able to find those people. And when I do find them, I got to have faith in them. And I think we succeeded in that, because we put together a pretty darn good team with a good mix, a good background mix of construction and design. And I think the project shows it.
And the cost? About $500 million. Now, just what is the Rogers Pass project? Well, this grade reduction project has 4 major features. A 15-kilometer surface route, a short tunnel almost 2 kilometers long, a 14-kilometer long tunnel, and a very sophisticated tunnel ventilation system. The project begins here, near Rogers Pusher Station, where the pusher locomotives are now added to each westbound train. From Rogers, the route of the project goes west, along the steep slopes of the Beaver Valley. This surface route is the first major feature of the project. On it, there are 4 bridges and 4 large concrete culverts on turbulent creeks and a steep gully. Finally, the surface route crosses a very long and complex viaduct structure. And from there, the route enters a short tunnel, the second feature of the project, which takes it under the Trans-Canada Highway. The route then crosses the 5th bridge on the project and continues for a short distance to Mount Macdonald, where it enters the longest railway tunnel in North America, the 3rd feature of the project. This tunnel ends here, at the base of Mount Cheops, almost 35 kilometers from where the project began, back near Rogers Pusher Station. And the fourth feature of the project? Well, because the tunnel is so long, almost 15 kilometers, it has to be ventilated. So a large ventilation shaft from the top of this mountain goes straight down to the tunnel, 350 meters below. This shaft is the key to a unique ventilation system that clears the air so that the maximum number of trains can use the tunnel each day. And that's the Rogers Pass project. A huge grade reduction program that will take more than 4 years of grueling work to complete. When the project is finished, the existing railway line will handle only eastbound trains going down its steeper grade. And the new line, with its reduced grade, will handle only westbound trains. Now, how did the work on the project begin?
Planning of Rogers Pass started back in, the mid-70s. So you can see it's been in the planning stage, really, at various levels for a considerable period of time. There were 4 different alternate routes looked at in the course of planning the actual route. The present route, that is the route that we finally constructed, was selected because it made the least effect on the environment. It allowed us to obtain the necessary grade that we wanted, and it was the best of the 4 for construction purposes.
There were extensive studies made of the proposed route. Studies of the terrain, geology, environment, wildlife, water courses, visual impact. And then, of course, there were the basic considerations. Can the project be built, and at what cost? There were a number of approvals required. The first was from the Canadian Transport Commission, a very lengthy procedure requiring public hearings. There were also 2 years of environmental hearings at various locations throughout Western Canada. And finally, because most of the project is within the boundaries of Glacier National Park, a great deal of work was done with Parks Canada before final approval was received. Meanwhile, exhaustive surveys had been done to assess the problems of construction in the area. Access roads to the working sites were pushed through, and some preparatory work was done. Contractors were then called in and given a thorough briefing and a tour of the site so that accurate estimates could be prepared and contracts awarded. At last, in 1984, the major work was ready to begin. The project was officially opened by President Russell Allison.
Good afternoon, ladies and gentlemen. I am proud and pleased to officially open the Rogers Pass project today. This is the largest construction project in the history of CP Rail since the actual building of the railway itself some 100 years ago. And so far as I'm concerned, it's almost as important. I must say that the work has well begun, and I'd like now to officially declare the Rogers Pass project underway, and it will be moving vigorously towards completion.
Major work on the project could now proceed. But there was still an important first step. The Rogers Pass project is not close to any town, so housing had to be provided for as many as 1,100 people working on the site. 3 camps were built at convenient locations along the project route, at Rogers, at Beaver Creek, and at Flat Creek. Gord Britton, camp manager CP Rail, supervises their operations.
CP operates the camps on behalf of the contractors. It would just be impractical for each contractor. We've had 17, 18 contractors on the site, and it wouldn't be practical for each one of them to provide accommodation for their workers. It's something like running a major hotel, but we have additional problems. We have to provide our own water services, our own sewer services, our own power, our own fire protection, and this type of thing. So we have accommodations. It's not home, but we try to make it as comfortable as possible. It's surprising some of the statistics on the food, although that's handled by the caterer. There's some 4,000 T-bone steaks a month, you know. 3,000 dozen eggs a month. Somewhere between 3.5 and 4 tons of vegetables. You know, it's a full menu. Something that should be mentioned is the safety that we have. I think we're very, very proud of our safety in camp. We probably have better protection here in camp than most hotels in Canada.
2 of the work camps are in Glacier National Park, so garbage disposal, snow removal, even their general appearance are strictly regulated. And when the project is finished,
The work camps, when the project is being completed, will be dismantled, and the sites where they're located at the present time will be completely reclaimed with grasses and trees.
now let's take a look at the first major feature of the project, the surface route. The surface route is the key to the whole Rogers Pass project. Near the end of its 15-kilometer length, the reduced grade will be lower than the old line by the height of a 40-story building. Let's take a look at just what that involves. Just west of Rogers Pusher Station is Cupola Creek Bridge, where the Rogers Pass project officially begins. Now you can see the position of the 2 railway lines, the old line on the right and the roadbed for the new line on the left. You can also see the grade reduction beginning to take effect already, as the old line, with its steeper grade, rises above the new line's roadbed. Now, let's see some of the construction challenges of this new surface route as we move westward. This is Alder Creek Culvert, which has already been completed and was a relatively straightforward construction. But here, the old line had to be moved back into the rock slope to make room for the new line between it and the Beaver River below. And here, you can see the very narrow right-of-way in which the work had to be done because of its location in Glacier National Park. Next is the site of the new Mountain Creek Bridge, which had some interesting problems to be solved. And just west of here is a major rock cut excavated to accommodate the new line. Opposite the rock cut, a huge embankment or berm will suppress the noise of passing trains at the nearby Mountain Creek campground. You can now begin to see the steep slopes over which the new line had to be built. Further west is the first of 3 concrete box culverts at Cedar Creek. Then another box culvert at Raspberry Creek, and a new bridge, Gully Bridge, over a dry gully. As we go west, the slopes and the construction difficulties become even more dramatic, as you can see. This is the 3rd and last concrete box culvert at Surprise Creek. Can you imagine a constant 1% grade built through this formidable terrain? The survey work has to be extremely precise. Next, the longest and highest bridge on the new surface route over Stony Creek. Then, as we continue westward, we come to the site of the viaduct, one of the major engineering and construction challenges on the project, with its incredibly difficult slopes. We'll see these features in more detail later. But first, let's hear from some of the men who planned and built this route. Here's John Fox.
Well, to engineer a project the size of Rogers Pass requires, 1, a lot of very competent people, and 2, the use of a lot of engineering know-how.
Ron Tanaka, Chief Construction Engineer, Special Projects, CP Rail, helps provide that engineering know-how.
All the engineering was done in Calgary before the work started. This began about 2 years even before construction began. The engineering work was done basically with the help of consultants All the plans and specifications and contracts were prepared in our Calgary office.
And Norm Tennick, construction manager, special projects, CP Rail, is the man who sees that these plans are properly executed.
My job is mainly to see that this project gets built, to put all the pieces together, to coordinate all the construction activities on site, including contractors, subcontractors, my staff. The surface route comprised about 10 miles of new grade construction, mostly a cut and fill job involving over 2 million yards of excavation, of which 600,000 yards was rock.
And traffic on the narrow right-of-way became an increasing problem. But meanwhile, a number of complex construction challenges have been met and overcome on the surface route. Remember its 3 concrete box culverts and 5 major bridges? Right now, we're interested in 4 of those bridges. The first is here at Cupola Creek. The challenge here was to keep trains running on the main line, while a new double-tracked bridge was built on the site of the old single-tracked one. So the old bridge was moved upstream out of the way, and trains were detoured over it while the new bridge was built in its place. The second bridge is here at Mountain Creek, 4 kilometers further west and about 40 meters below the old line.
The major considerations that you have to be aware of when you're designing a bridge over streams, and in particular, I guess the streams that are in Glacier National Park, you have to make sure that no part of the structure is within the wetted perimeter of the stream that you're working on.
That, of course, is an environmental protection measure. And as a result, one of the piers here at Mountain Creek had to have a specially lined dike built around it to prevent muddying the water during construction. The bridge has 2 48-meter spans, each weighing 250 tons, the heaviest on any of the bridges. Next is Gully Bridge, about 9 kilometers from the start of the project. Gully Bridge, like all the new bridges on the surface route, was given a protective treatment of waterproofing before finishing. Now, about 13 kilometers along the route, we come to Stony Creek Bridge.
The Stony Creek Bridge is the highest and longest of all the bridges on the surface route. And because it can be seen from the Trans-Canada Highway, a lot of planning went into how it would look.
As you can see, Stony Creek Bridge was a major construction challenge. Work on the bridge began in 1984.
The span that crosses over Stony Creek itself is an extra long span that it's about 170 feet in length, and it was put there really to ensure that the piers on which it sits was not in the wetted area of the stream.
Greg Hamilton, project engineer, special projects, CP Rail, hasn't forgotten those bridge spans or any other bridge spans on this project.
The one problem we did have with all bridges was movement of the spans to the site from the highway. In some cases, we had to get special permission from the Parks Canada people to cut down additional trees outside our right-of-way in order to move the spans to the site.
But in spite of the difficulties, Stony Creek Bridge and all the other bridges were finished on schedule. But there are other creeks on the surface route with a different kind of challenge. Ron Tanaka explains.
A unique feature of the project would be the construction of what these three large box concrete culverts. When you look at the size of the stream during the summertime, it's only a trickle of water, and you wonder why the engineers would design this huge structure. And this structure is about 10 feet high, and some are 10 feet wide and 20 feet wide. And it doesn't seem to make sense to build this huge waterway for a little stream. But when you realize that during the spring runoffs, it's not just the water, but all the debris that's coming down onto this, from this valley, you realize we do need this kind of a culvert. Another thing which is interesting, that inside these culverts we have these concrete energy arresters, which look like a series of tombstones when you look at them, and the whole purpose of it is to dissipate the energy because of the steep of the culverts and the amount of water and debris coming down the culverts. If you don't stop the energy of the water, then it would cause erosion on the downstream end.
So you see that crossing a tiny mountain stream is not a simple matter. But that was only one of the many challenges on this project.
Well, of course, the visual impact of a job of this size is important. And one thing that we did do, which I think was a first, was use a computer to indicate to us what it would look like after we were finished. And from this, you could really determine the actual visual impact of what it was we were going to do. Retaining walls are used in areas where you don't want to carry out huge cuts, either uphill or large fills downhill, which would become visible in terms of impact to visitors to the park and ourselves, for that matter.
Well, in our case, the main factor influencing use of retaining walls would be the slope of the terrain we had to excavate through. Being roughly 40 degrees, if we allowed for the excavation wall to be on its natural slope, it would have undermined the existing main line. So we needed a vertical, most vertical type of retaining wall possible in order to prevent that. On the downhill side where we have our fills, without a retaining wall, the fill would have encroached onto the Trans-Canada Highway or the Beaver Valley down below.
There are a great variety of different types of retaining walls, and in our case, we used what we call shotcrete walls for uphill retaining walls, and we used what we call a precast type wall, tied back type wall for downhill.
The Type 1 retaining wall is basically two 2-inch thick layers of shotcrete reinforced with welded wire mesh. The Type 2 wall is similar, except that there are ground anchors installed on a 7 by 7 foot pattern. Basically, the Type 3 wall is a series of precast soldier piles standing at 10-foot centers along the downhill line. It is a downhill retaining wall. And then lagging precast segments of lagging are installed between your soldier piles, and then the entire area between the original ground and your retaining wall is backfilled with local material to create a new subgrade.
The three major type of walls that we use, I don't think they're absolutely unique to Roger's past job. They have been used in the past on other projects. I think the extensive use that we made of them is perhaps unique.
It involved about 230,000 square feet of retaining walls with about 120,000 lineal feet of ground anchors to support them.
And mainly it was because of the necessity to keep the right-of-way as narrow as possible going through the national park.
And next, that narrow right-of-way presented the greatest challenge of the whole Rogers Pass project, the 1,200-meter-long viaduct. Take a look at the problem from the air with Ron Tanaka.
The viaduct is a unique solution to the challenge of the terrain. The slopes at 40 to 42 degrees are steeper than anywhere else on the surface route. You see, the ordinary cut and fill methods can't be used because they would undermine the existing track, and the new downhill slope would extend over the Trans-Canada Highway where it approaches the new line.
And here's John Fox on the subject of this most difficult part of the project.
The toughest part of the route to engineer was actually the viaduct and how we could be able to locate the piers on the very steep slopes and keep them there after we got trains on them. And that required a lot of head scratching and soul searching as to the correct method. It required some very precise survey work to establish the actual elevations of the ground and the center line of the structure itself.
The main concern in trying to design the viaduct was to try to design a footing on this 40-degree slope. And the main difficulty in trying to do that is because of the 40-degree slope, there are side hill movements. And it's trying to design a footing to counteract this tendency of the mountain to move downhill on this 40-degree slope.
Trevor Webster, Deputy Chief Construction Engineer, Special Projects, CP Rail, explains how this was done.
Each pier will be built on a concrete footing and will be tied back into the slope with ground anchors. For additional stabilization, steel micropiles are sunk from each pier 10 to 15 meters into the ground.
Access had to be maintained to every single pier in order to construct it. And each pier was at different elevations and up and down through gullies and hills, and access was extremely difficult.
Let's see how it was. First, the stabilizing ground anchors and micropiles were drilled and installed. As many as 30 micropiles for each individual pier. Then forms had to be built for every one of the 44 piers, every one at a different height and in different conditions of slope and soil. Tons of concrete were moved in over the twisting tracks cut into the narrow slope. And finally, after 3 years of grueling work, the very precise construction of the whole kilometer-long viaduct could begin to be seen in this restricted and unfriendly terrain.
An interesting feature of the construction of the viaduct will be the erection of the spans.
The method of installing the 45 spans on the viaduct was done by means of what we call a launching machine or a launching bridge.
The spans arrived by rail and were offloaded at the west abutment of Stony Creek Bridge and loaded at that point onto a truck with a steerable dolly. The truck then backed across the completed grade to the viaduct and then approached the underside of the launching truss which sat on the viaduct. At that stage, it backed underneath the launching truss. The launcher picked the span. The truck then drove back to the west abutment of Stony. The launcher then advanced the new span on a trolley system to its final location, lowered it in place, and then the whole launching truss advanced onto the newly installed span and awaited the next delivery. Launching spans actually proved to be one of the brighter lights on this project. It went very well. The superstructure was constructed in 1 month.
Insofar as the surface route is concerned, when we put the last span in that viaduct, the 45th span, when it went in, we broke open a few bottles of champagne that day. And that was a real highlight.
Well, you've seen the struggle with nature on the surface route, the building of its bridges, culverts, retaining walls, and the biggest challenge of all, the viaduct. But how did the environment come through all this? Let's take a look. Remember this? Well, this is how that same area looked soon after the viaduct was completed. And now John Fox talks about the environment, its protection, and the reclamation of it that you see here.
The size of our Rogers Pass project meant that we were disturbing a very large part of the environment, and it required constant looking at on our part to ensure that we were living up to all the requirements of good environmental protection. While you're actually doing construction work, you have to worry about the environment and watch such things as oil spills, fuel spills, particularly from equipment that's working. You have to worry about bulldozer operators pushing fill or refuse into rivers. You have to worry about garbage around the construction site. And we have people constantly watching for this sort of thing to ensure that doesn't happen. The main purpose of reclamation work is to ensure slope stability. In addition to that, you have a responsibility when you go in and disturb land to restore it as near as you can to its former looks or beauty. In our case, it's beauty. And we have no right to go in and destroy something and leave it that way.
Dave Polster, Environmental Supervisor, Special Projects, CP Rail, tells us how the environment is restored.
We'll be reclaiming continuously here as the grade is built. We'll get right in right after sections are completed, and even before the entire section is completed, we'll be reclaiming on the job. Parks Canada and CP Rail have reached an agreement regarding all aspects of the job, but particularly the environmental aspects, and we have a very rigid set of standards which we have to adhere to. We'll be involved in planting a cover of grasses and legumes that will control erosion, and then trees and shrubs which will reestablish the natural patterns of tree and shrubs in the area. The key to revegetation in this area is going to be fine textured material, and that is why we've ensured that we have top dressing applications in areas where we need it. Also, the steep slopes are another aspect of the reclamation program which is a little bit unusual from the normal reclamation work. We expect that we'll be using somewhere in the neighborhood of 30,000 pounds of grass and legume seed and about 100,000 pounds of fertilizer. We've ordered well over 600,000 trees and shrubs to be used in the reclamation project. Exact formulation was worked out between myself and Parks Canada in terms of enhancing wildlife values in certain areas, trying to keep wildlife away from other areas, things like erosion protection, and getting the new grade to look like the surrounding terrain. Certainly the environmental aspects of the job are built right into the heart of the project.
And Parks Canada has used it, I understand, as a standard for future projects of this nature.
Reclamation work won't be considered finished until at least 5 years after construction is complete. And it will cost CP Rail several millions of dollars. But now let's move on to the second major feature of the Rogers Pass project, the short tunnel, or the Mount Shaughnessy Tunnel, which goes from the viaduct to here, just across the Trans-Canada Highway. And why a tunnel? Listen to John Fox.
Well, the first thing we looked at when we were in the design stage was how we're going to get across this Trans-Canada Highway. And we had one scheme where we would have come across the highway about halfway up the hill on a very, very high bridge. The big problem with that was snow, besides visual impactment on the valley. But we would have been plowing snow off a bridge and right onto the highway, and Parks Canada wouldn't have thought too much of that.
The answer to this, of course, was a tunnel under the highway. And this is some of the early work at its eastern end, just beyond the viaduct. The tunnel goes under the shoulder of Mount Shaughnessy for 1.8 kilometers. And it comes out here below the Trans-Canada Highway. But curiously enough, the tunnel was built from this end back to the east end. Pete Penner, Tunnel Superintendent Special Projects, CP Rail, tells us why.
Access to the east portal of Shaughnessy was very restricted because of the construction of the viaduct, and accordingly the contractor had to drive the tunnel totally from the west end.
So only external work on the east portal was done. But the tunnel coming from the west had to meet that portal dead on. Getting equipment and materials into this site was always a very difficult task through the congestion of other work on the surface route. Meanwhile, at the western end of the tunnel, work began with the construction of the Connaught Creek Bridge, the fifth and last bridge on the project. It had to be built first to provide access to the working face of the tunnel. But remember the Trans-Canada Highway just above the west portal? Here's Ron Tanaka to tell us about the challenge that gave to the project planners.
From our geotechnical investigations, we knew that each end of the short tunnel would go through overburden. As a matter of fact, on the west side, we go right underneath the Trans-Canada Highway through an overburden section, and the depth of soil between the Trans-Canada Highway and the top of the tunnel is only about 40 feet. We were always concerned about this because in most tunnels going through overburden, there is always the possibility of subsidence or depression of the surface above, and in this case it was a Trans-Canada Highway. What we did was to grout the soil between the Trans-Canada Highway subbase and the top of our tunnel, so that when we went through with our excavation, there was basically a massive grout, not soil anymore, it was consolidated grout, so that prevented any settlement of the Trans-Canada Highway.
After that, building the tunnel could proceed. The west portal was finished, and inside the tunnel became a typical mining operation. It was built by the top heading and bench method. First, the top half of the tunnel is cut out and reinforced with steel ribbing and shotcrete where necessary. Then the benching operation removes the bottom half to complete the full depth of the tunnel. But unfortunately, it wasn't all as simple as that. Listen to John Fox.
The short tunnel gave us some real problems this past year in terms of soft rock, which we knew was there from the investigations we did. What we didn't know was it was going to come down on top of us after we passed it, requiring extensive support systems to be put in the tunnel and also a concrete lining in an area which we had not considered in design.
Nevertheless, the short tunnel, or the Mount Shaughnessy tunnel to use its proper name, did get built. And here, John Fox and Pete Penner are looking over another interesting feature of the tunnel work. At this point, we're between the two tunnels of the project, the short Mount Shaughnessy tunnel that we've just seen and the much longer Mount Macdonald tunnel just ahead. Between them is a short section of surface route, not quite 1.5 kilometers long. But in that short stretch is a huge depression known as the Bear Pit, and the new railway line will have to cross it. It will take about 400,000 cubic meters of material to fill the Bear Pit. And where do you think all that fill material will come from? Right, from the two tunnels. So this is one depression that serves a useful purpose. If it hadn't been here, all that rubble, or tunnel muck as it's called, would have had to be removed from Glacier National Park for disposal somewhere else. And of course, when reclamation is finished, the whole area will look a lot better than it did before. as you can imagine from what has already been done. But now, let's get on to the third major feature of the Rogers Pass project, the Mount Macdonald Tunnel, or the Long Tunnel, which goes under two mountains and is the longest railway tunnel in North America. The Long Tunnel begins here at the eastern end of Mount Macdonald. It goes under the mountain, under Rogers Pass, and under Mount Cheops to come out here, almost 15 kilometers from where it began. The new tunnel will be 109 meters below the old Connaught Tunnel and 290 meters below the summit of the pass. But the very length of the tunnel created some problems in construction.
It was necessary to excavate the long tunnel from both ends, really to save time in terms of getting the job done.
Because of the length of the Mount Macdonald Tunnel, it would have not been practical to do the excavation and concreting completely from one end. The entire tunnel is about 47,000 feet long, and doing it from one end would have taken about 5 or 6 years. Plus the fact by cutting it from each end, we were able to give it to 2 contractors, and there's always this feeling of competition between contractors to do a faster and better job, and this, I think, aided in the progress of the work. Another thing, too, we had to consider was that if one contractor doing it from one end encounters some geotechnical problems, the entire rest of the tunnel would be delayed. By cutting it from 2 ends, if one contractor had a problem, the other contractor probably would have been able to continue.
And how would the contractors cut the tunnel?
Construction methods used in excavating the long tunnel were really left up to the contractors. We, that is the railway company, we didn't dictate how they could do it. It was left up to the contractors themselves. And really what dictated the different methods was the type of rock. The 2 methods used to excavate the tunnel on the east end, the contractor elected to use a 22-foot diameter mole to take out what we call a top bench, and then come in behind and take out the bottom bench to give us the shape of tunnel which we wanted. Whereas the contractor from the west end, he decided to go full face and excavate the entire face as he went in one shot.
So we have 2 sides to the Mount Macdonald Tunnel and 2 different construction methods, and maybe even a race to finish first. Now, here's the east portal of the Mount Macdonald Tunnel, way back in 1983. Let's watch it progress. Work started on the east portal in August 1984, with the first blasting into the rock face. The tunnel began with the conventional top heading and bench method for a short distance into the rock, and work was started on the portal structures. Then, in late 1984, the star of the tunneling work at the east portal arrived and was assembled in the snow. This was the tunnel boring machine, or the mole, as it was called.
The biggest problem was that the contractor was assembling a white painted mole in the middle of the winter, which made finding parts somewhat difficult at times.
But driving a tunnel through the rock of the mountainside did present some greater challenges than that.
The kind of information we need in designing this long tunnel is basically all kinds of geotechnical investigation. We have to find out whether the tunnel is going through overburden or it's going through rock, and also trying to determine what kind of rock is going through, whether there are faults, whether we're going to hit water, whether we're going to hit gases, all these things which in tunnels you always encounter. We get this information basically by 2 methods. The first thing we did is to go out and examine the surface, and by examining the surface contours and the ground types, and also the location of faults at the surface, the geotechnical people are able to predict whether we're going to hit these faults down below or not at tunnel level. The second thing we did was to drill a series of diamond drilling holes to examine the type of rock or soil in which the tunnel will be going through.
The long tunnel, Macdonald Tunnel, is a 47,000-foot tunnel driven in phyllites, which is a very soft rock, and quartzite, which is very hard. Most of the pilots are in the eastern section, so the contractor chose to drive a top heading there with a TBM, 22 foot 4 inches diameter, and then take out the bottom by conventional drill and blast or benching operation.
Finished tunnel will be 5.2 meters wide and almost 8 meters from rail to roof. And it will be concrete lined, lighted, and ventilated. Okay. Okay, we'll go inside and take a look at the rock in here and see how far we're at, what problems they got, if any.
The mole, with its rotating cutter head, is working at the face of the tunnel. It bores a hole about 6.7 meters in diameter. The main difficulty in constructing of the east portal, or the east section of the long tunnel, is its length. The total length of this contract was 27,400 feet, and the difficulty in these longer tunnels of 5 miles or more is the transportation of all the men, the materials, the muck coming out of the boring machine, the explosives when we start drilling and blasting the bench, the concrete, and it's the organizing of the transportation and handling of materials. That becomes the main problem. The mole is about 18 meters long and weighs over 300 tons. Up front, on the rotating cutter head, there are 52 cutting discs that grind the rock into small pieces which are scooped up onto the conveyor system for loading on the muck train. 2 muck trains are in operation, one being loaded while the other one empties. The mole can be steered through curves and adjusted up or down to ensure an accurate heading.
But the mole did have some difficulties.
The bearing came apart on the mole and caused about $1 million damage to the machine, and lost 2.5 months getting it repaired. And after that, we were concerned that the mole would stand up for the rest of the excavation. There were still 3.5 miles ahead of us. The rock was better than anticipated, and the mole, in spite of the 2-month breakdown, it did finish tunnel boring on schedule. When all systems were working, the mole would average possibly 140 to 160 feet on an average, about 150 foot average. Its best production, we set a record for that size of mole in this kind of hard rock of 206.3 feet in one 24-hour day.
So the mole bored 5 miles into the mountain, right on schedule. But how do we know it's going to meet the half of the tunnel that's coming from the other end?
The tunnel alignment in terms of accuracy of meeting was established by doing a very precise type survey initially outside to establish the proper locations of the portals, and also benchmarks to work from. And during the course of construction, the same precise survey was carried out underground from both ends. And using this precise survey, the laser beams used to direct the actual tunneling operation were set from that, and we met.
Rob Simmerling, Survey Engineer Special Projects, CP Rail, was the man responsible.
So, how's the alignment coming today there, Tom? Half an inch high. To check on the accuracy of the tunnel, a survey is done by CP Rail every 240 meters that the tunnel advances. This survey is performed with electronic theodolites to check the alignment and height of the recent event. Satellites were recently used to check the primary surface control points at both the east and west portals. This is the first time that global positioning system satellites have ever been used in an underground mining operation. From these satellite-verified surface points, the survey control is brought forward to the working face by conventional survey methods. This survey control is then used to align the laser beam that guides the mole.
The tolerances that we specified in the contract was 2 inches. The meat had to be within 2 inches vertically and 6 inches horizontally.
Well, we know we're heading in the right direction. So when the mole's work is done here in the east portal side of the tunnel, we can go on to the next step, the benching operation.
The benching in the east portal entailed taking out the bottom 11 feet of the tunnel. The mole bored 22 feet, and in order to get the tunnel configuration we wanted, a square section had to be taken out of the bottom of the tunnel. After benching's completed, the contractor has to go in and backfill the sub-invert and install the drain pipes. Then he's pouring what we call a pony wall or a starter wall in order to align his main arch form, as well as the starter wall embeds all the electrical utilities and services we require for the permanent tunnel operation. After the pony wall is poured in the east tunnel lining, the contractor is using a traveling form so that the concrete is advancing continuously. He has a 288-foot form which keeps moving ahead of itself. Sort of an inchworm principle, you could call it, I guess.
Now, did all this work on the tunnel have any effect on the environment?
The construction of the tunnel basically would affect the water courses in and around the project, and mainly because of the ammonia that released from the blasts of powder that were used in excavating the tunnels.
We have at each portal of the tunnels a huge wastewater treatment plant, and all the water coming out of the tunnels, which do have some silt and some oils in them because of the construction activities, are cleaned out before they enter the stream and the parks.
Water that is returned to the environment from the tunnels, or that is affected by any work on the project, is constantly checked. Air and water tests are conducted at as many as 44 sites within the project boundaries and analyzed at the project lab. In addition, vital tests of the various processes of construction are carried out in the lab and on location throughout the project. Now let's go on to the west portal of the long tunnel. As we leave, we'll get a good view of the east portal. This is the summit of Rogers Pass. We're roughly following the direction of the long tunnel, which is about 340 meters below the slope of the mountain. And here's the west portal, coming out of the mountain below Mount Cheops, 14.7 kilometers from the entrance. You can get a better idea of the size of the tunnel from this angle. It's much bigger than it looks from the air.
Here we use the drill and blast tunneling technique, which is standard mining procedure. Okay, Ron, let's go. We'll go inside and take a look in here.
Now this is the way the finished tunnel will look. Lining is done with a movable 25-meter long steel form. Concrete brought in by rail-mounted agitator cars is pumped in behind the forms to build the finished walls and arch of the tunnel. On average, 15 meters a day can be completed by this method, with crews working in 3 shifts, day and night.
You see the difference in the two tunneling techniques. At the east portal, we saw an unfinished tunnel until the very end of the work. Here at the west portal, the finishing of the walls and arch progresses as the tunnel is cut forward. Then we come to the unfinished part of the tunnel. Let's listen to Ron Tanaka.
This is the beginning of the process of drilling, blasting, and mucking out the rubble. The jumbo drill cuts 100 holes about 4.3 meters deep into the rock face. The drill holes are filled with explosives and blasted out. The blast loosens the rock, and then the loader moves in to remove the rubble. So with this technique, in 3 shifts a day, about 4 cycles of drilling, blasting, and mucking can be done. This advances the tunnel about 15 meters each day.
The actual construction progress of the tunneling was monitored on a day-to-day basis by my own engineers in the field, and of course precise records have been kept of the actual daily footage that was accomplished.
Staff geologists map the rock in the tunnel every day. It provides a necessary basis to determine permanent support for the tunnel rock. From this mapping, the geologists then decide where to place rock bolts to reinforce the tunnel walls.
Because rock is not a homogeneous medium, rock bolts are used to stitch it together.
Okay, if rock bolts are used to reinforce the tunnel, why does it have to be lined? The short tunnel isn't lined.
The lining in the long tunnel is required strictly for ventilation purposes. It's not a structural lining. There's no reinforcing in it other than in a few places where we have less than adequate rock support. But generally, it is strictly to make a smooth pipe for airflow.
We'll come back to that airflow later. But now, what about lighting? Does a tunnel really need to be lighted?
Tunnels generally are not illuminated in North America. They're generally quite dark. And when it comes time to do any work in them, you have to take in either portable generators or whatever to provide the light for the workmen to work in. And it's really, it's not the way to work. And when we designed the Mount McDonald and Shaughnessy Tunnel, we'd made up our minds we had to have power up there anyway. So let's put some lights inside so at least our maintenance away people can see what they're doing.
Well, the tunnel work progressed on schedule from each end. And who won the race to the center? At the east side, the mole reached its end first, but then the tunnel had to be benched and lined. The west side reached its end a couple of months later, but the tunnel form was closer to finished when it got there. But even more important, both sides did meet right on schedule on October 24th, 1986, about 25 months after work began.
There are a number of highlights of the project that I've experienced to date. And I guess probably the one that sort of holds top place in my mind has to be the breakthrough of the 9-mile Mount McDonald Tunnel. That was quite a day when they blew the last plug out and you could see out from one end to the other. They're too long for that, but it was nice to be able to see the other side of the tunnel.
I'm talking to some of the miners there, and one of the guys said to me, "What are you going to do when we have the breakthrough?" And I said, "I'm going to get the biggest damn bottle of champagne that I can find in our country," and I said, "I'm going to give it to you guys." So I got it, and it's right there. Now I'm going to ask Steve and Peter and Ron if you'll come forward, and you guys can open that damn bottle, and I don't want to see anybody but a miner drink it, okay?
And of course, there were more formal ceremonies at the breakthrough.
We're about to mark a significant event in CP Rail's Rogers Pass project, the joining of the east and west sections of the Mount McDonald Tunnel. It is with great pride of accomplishment that I am about to detonate a charge that will break through the final 100 cubic meter wall separating the two sections of this project. CP Rail now has the longest railway tunnel in North America.
The surveyors were the guys that made that damn tunnel meet. Don't ever forget about it. And I'll tell you, there were a bunch of them here this past week that were doing a wee bit of sweating.
So, now we've got the longest railway tunnel in North America. But that distinction gives us a brand new challenge.
Because of the length of the tunnel, we had to design a cooling system to provide cool air for the locomotives, and also a purging system to purge out the diesel or the foul air from the tunnels. In a shorter tunnel, you don't have to do that.
The ventilation system for the long tunnel is the fourth major feature of the Rogers Pass project. It is very sophisticated and is the only one of its kind in the Western Hemisphere. It has three key elements: a divided vertical shaft from the top of the mountainside to the tunnel, an arrangement of very powerful fans for pushing and pulling air through the tunnel, and two automatic gates which control the flow of air in the tunnel as trains pass through. As the train approaches the tunnel from the east, the portal door opens, and a cooling flow of air is drawn from the ventilation shaft and pushes exhaust gases out through the portal. At the center of the tunnel, the automatic door lets the train through, but then closes again as a cooling flow of air is drawn from the west portal and out the ventilation shaft. For cooling and purging purposes, the long tunnel is effectively divided in two, which means that the operation can be done much faster, and trains can pass through at intervals of about 35 minutes. This may sound like a long time between trains, but a unit coal train with more than 100 cars will take about 30 minutes to pass through the tunnel. So you can see that the operation will be very efficient, and it's expected to increase daily westbound capacity from the present 15 to at least 24 trains per day. But building the 350-meter ventilation shaft for this system was a challenge all its own.
In the design of all shafts, most designers try to find an area where there is as little overburden as possible. And this is because excavating and trying to construct through overburden in a shaft is very expensive. The initial location we had in our choice of a selection for a shaft was an area which was where the rock was exposed to the surface, which would minimize the amount of overburden we had to dig through. Unfortunately, this was located in an area in the park which is very visible to the Trans-Canada Highway. Therefore, in order to make our agreements with Parks Canada, we had to select another location which was in a treat area which was not visible from the highway, but we had 300 feet of overburden to excavate through. In excavating the shaft, the most difficult geotechnical problem to overcome is the infiltration of water. And it's not just the quantity of the water, but it's the mixture of the water and the type of soil which seeps into the excavation. And it makes it very difficult to support the walls of the excavation while the construction is going on.
In sinking through the overburden, we encountered water problems that the contractor could not handle, and consequently we ended up having to freeze the last 150 feet of overburden in order to excavate through it.
This was done from the inside of the shaft, which to my knowledge was the first time that a shaft of our size had ever been frozen from the inside.
This involved drilling 48 holes on a fan, fanning out from inside the shaft to form a perimeter of freeze holes, pumping brine through the holes and freezing a 6-foot thick ice wall minimum, and then sinking the shaft inside this ice wall. Most of our problems were in the overburden, but after we got through that into the rock, progress went very well.
As we have seen, the ventilation shaft has a dividing wall separating the east and west ventilation functions. And it's connected to the main tunnel by two smaller air tunnels. Between these, in a huge chamber over the main tunnel, is the 80-foot gate building, which is part of the ventilation system. Back on the surface, at the top of the ventilation shaft, is a very large building which houses 4 huge fans and the computer controls for the ventilation system. And as we know, the visual impact on the environment is very important on this project.
The ventilation building is located at the top of Rogers Pass in a very sensitive area. And to make sure that no part of the building was seen, what we did, we located it up on the slope away from the Trans-Canada Highway in an area where we have trees in excess of 100 feet in height. And the building being only some 70 feet high, of course you can't see it.
Meanwhile, back on the surface route, the railway line was being laid for today's traffic and for the future.
The ties, the ties and rail have been designed for the heaviest cars that we operate and will operate in the future. So yeah, it'll take care of future traffic. The track structure which we'll put in on the surface route will consist of concrete ties. They'll be spaced roughly on 2-foot centers except for curves where they're spaced a little closer. It'll have a 136-pound welded rail. It'll be held in place on the ties by spring clips. The track will be ballasted with a good quality rock ballast.
Well, the old system of wooden ties and iron spikes is gone. From the Rogers Pass project, anyway. It's the largest installation of this new system on CP rail.
The advantage of a concrete tie track mainly is one of less maintenance. You don't have to change ties. The question of changing rail is made easier and cheaper. And again, it's a cost reduction as far as maintenance is concerned project.
And how about the tunnels? What will the rails be laid on in the tunnels?
Pack track, which we're going to use in the tunnel, will be used only in the tunnel. And the main reason for it being used only in the tunnel is that it's on a rock surface, and that gives you the maximum support. If we use it on any part of the surface route, then we have to, in addition to the actual pack track itself, we'd have to lay a very thick base slab, which is extremely costly.
Ed Taylor, supervisor, track design and development CP Rail, was involved in testing the pack track system for the railbed before the final decision was made to use it.
Pack track really is paved concrete track. Consists of 2 concrete structures, base slab and top slab, with continuous CWR rail, and essentially it's to use primarily in tunnels. The idea is to get it established and determine its validity before it's installed in the tunnels at Rogers Pass project. Perhaps the integrity of the entire Rogers Pass tunnel project is based on how well the track performs. Well, we're evaluating the entire structure. That is, reinforced concrete base slab, top slab, the fasteners, the method by which they're held, and rail life.
The test section of pack track performed very well, and so it was installed as the rail bed for the track in the tunnels. Let's let John Fox have the last word.
The main advantage of using a pack track is the fact that there's very little or no maintenance required over the years that it'll be in service. There's no ballast to change or no ties to change. no spikes, no tie plates. It's virtually a maintenance-free system.
So with the new track laid on the surface route and in the tunnels, the Rogers Pass project is now almost complete. But first, the whole system on the new line has to be checked out in operation.
A new line of railway is always inspected before you put it in service. And the major reason is to ensure that the line is properly built and is built to the proper standards. In addition to that, you want to ensure that all aspects of safety are covered. When we open the line up for traffic, that is regular traffic, we don't expect to do any further testing on our new line of railway. It should be in proper operating condition when we say go. You look at pretty well everything that comprises a piece of railroad. You check the turnouts and the switches, the rails, the wells, how the rail is fastened to the concrete ties, bridges, culverts, the entire structure of the railway. You inspect all monitoring equipment, such as hot box detectors, dragging equipment detectors, high wide load detectors, CTC signals, power switch machines, and so on. The new grade will handle 15,000-ton trains with 5 3,000 horsepower units without any problems. We know this because we operate such trains on such grades at the present time. We don't anticipate any unusual problems. This is heavy snow country, and you might have some problems with getting rid of snow. All structures on a new line are inspected to make sure that they're properly built. We won't be watching any particular part of this new line any more closely than we inspect any other part of our railroad. The viaduct is essentially a series of 90-foot bridges, and we don't have to do any particular type of tests other than put the thing together properly, which we've done. Our design and construction techniques were such that all we require is an annual maintenance inspection, which we do on a normal basis.
When we go through the short tunnel, you'll see the difference between it and the long tunnel. Remember, the short tunnel isn't ventilated, so it doesn't need a full lining like the long tunnel does to help the flow of air in its ventilation system.
Of 40 years service on the railroad and the trackage that I've been over, I would say this is the best piece of track that I've worked on.
When a train approaches the portals, it's on what we call a signal circuit. And in the signal circuit, there's also a circuit that will actuate the door mechanism.
The mechanism that opens the portal door is an electric motor with a chain drive to the shaft of the door, which raises the door up and down in a guillotine-type fashion. The portal door takes about 15 seconds to fully open up.
Ventilation system is tested by operating the fans in the various modes that they're designed to operate in. We'll know if the system is working properly on a regular basis by the length of time it takes to purge the various segments of the tunnel. There are 2 doors at each location, that is the east portal and the mid-tunnel gate. And if you lose power to one, you have a second one to fall back on. Throughout the tunnel, we have nitrogen oxide detectors and haze detectors, which will automatically tell us the condition of the air in the tunnels. Trains can be operated through the tunnel if the ventilation system is not working, but on a much slower basis.
Well, now we've seen it all, and we know it works. The surface route, with its lesser grade, its culverts, its bridges, and the spectacular viaduct. The short Mount Shaughnessy Tunnel, and the Mount McDonald Tunnel, the longest railway tunnel in North America, and the unique tunnel ventilation system. That sums up the Rogers Pass project. All 35 kilometers of grade reduction built to increase CP rail traffic capacity westbound. And now what's next?
Well, the last thing that we'll do so far as the whole project is concerned is put in the last clip and the track structure at the west, near the west portal.
November 9, 1988, marked this long-anticipated event. The end of 5 years of hard and dedicated work by hundreds of people. Most of those workers have now moved on to new challenges. But many return to ride a special train over the new line to its western end. And what could be more appropriate to celebrate the end of construction in these mountains than a little mountain music?
There's your alpine horns.
Good morning, ladies and gentlemen. What do you think of that train ride? In a few moments, we'll attach the last railway clip to a concrete tie. But before that, I would like to personally thank each of you for coming out today to witness the event and for being part of it. Our children and their children can look back and say that their father or mother worked on this project. History will show that the Rogers Pass project really is an engineering and railway marvel, unsurpassed for its time. Now, ladies and gentlemen, it is with the deepest respect and pleasure I call upon a true Canadian railroader and an engineer in his own right, Mr. Russell Allison, President of CP Rail, to say a few words. Mr. Allison.
I'm sure this historic moment is a proud one for everyone here today. It is for me. Very soon, the biggest CP Rail construction project in the last 100 years will be completed. I expect all of us, train crews included, will soon find it hard to imagine how we ran the railway in these mountains without the operating improvements this project makes possible. It'll be a lot easier and a whole lot better.
Now the moment has come. Mr. Allison, if you will join me in front of the podium, we will attach the last clip. Ladies and gentlemen, the last clip is attached. Construction of the Rogers Pass project is now complete.
And so we are witnesses to history. The successful completion of the Rogers Pass project is the CP Rail response to the transportation challenge of tomorrow. But even more important, in the railway's proud tradition, it's the answer of its people to nature's challenge here today. More than 100 years ago, Van Horn, the legendary builder of the railway, spoke for his time and ours.
All I can say is that the work has been well done in every way.
Well, John, how does it feel to be the Van Horn of the 20th century? On May 4th, 1989, the Rogers Pass project was officially opened. The opening ceremony was held at Frayne, British Columbia, the railway's name for the site of the start of the project at Cupola Creek. Many employees and a trainload of special guests arrived to take part.
Good morning.
My name is Barry Scott, and I'm the Chairman and Chief Executive Officer of the Canadian Pacific Railway. I'm delighted to see so many CPR employees, and delighted also that they brought their friends and families here so that they can see what's been going on these last 5 or so years. Rogers Pass was, in a sense, the last great bottleneck on our line. Today, instead of 15 trains, we can move as many as 24 a day from Calgary to Vancouver. And this is really a tremendous accomplishment, and one that means our customers will be able to move their goods to the markets of the Pacific Rim more efficiently than ever before. I think it's appropriate that we have with us today Charles Mayer as the Federal Minister of Western Economic Diversification.
The day belongs to Canadian Pacific. And we all know that if we don't have reliable transportation, not only for grain, but for other economic development and diversification, you can literally choke off any development before it even has a chance to begin. So the completion of the Rogers Pass project, I believe, is an historic occasion for our country, and it is not only historic in one sense, it is very vital in another. Congratulations on meeting the challenge. And now I'd like to read a very brief note from the Prime Minister. On behalf of the Government of Canada, I would like to convey my warmest greetings and sincere best wishes to all those attending the ceremonies marking the opening of the new Rogers Pass line. It will stand as a triumph of Canadian engineering and serve as testimony to the planners, builders, workers, and others who created this vital link. This historic trip recalls the importance of the hammering out of the last spike and launches us into a new era of rail freight transportation. Signed, Brian Mulroney, Prime Minister of Canada.
British Columbia and Canadian Pacific have a habit of celebrating major events together, and we wouldn't feel right about proceeding with this line without some encouragement from a representative of British Columbia. Neil Vant, Minister of Transportation and Highways, I'd like to introduce him to you.
CP Rail was instrumental in British Columbia entering Confederation 118 years ago. Since that time, Canadian Pacific Railway Company has created thousands of jobs for British Columbians, both directly through rail operations and indirectly through the movement of freight and goods into the province. This major capacity upgrading that we are celebrating today is vital to our economy.
Now I'd like to introduce Bill Stinson. I don't think Bill perhaps needs much introduction, but he is Chairman, President, and Chief Executive Officer of Canadian Pacific Limited, our parent company. And Bill, we have a job for you right now. We figure you can carry out this special task as honorary conductor of the Rogers Pass Inauguration Special, as long as you're properly supervised and look like a railway conductor. Bill, you're in charge.
CP Mountain Sub-Dispatcher, Revelstoke. This is Conductor Stinson on CP Passenger Extra 5903 West, over.
CP Passenger Extra 5903 West, this is CP Mountain Sub-Dispatcher, Revelstoke, over.
CP Passenger Extra 5903 West is located on the north track at Frayne and ready to proceed westward on the McDonald track, over.
Conductor Stinson, Passenger Extra 5903 West, this is your authority to proceed on signal indication, and your train will be operating on the McDonald track. Have a good trip, CP Mountain Sub-Dispatcher, Revelstoke Road.
In a few minutes, we will be reboarding our train, those of us who are going to proceed onward from here. But I don't want to leave here today without paying tribute to what I think is the company's greatest asset, and that is all of the people of the CPR. The people who day in and day out, you and others, make the railway run and do so with great success. We think our employees are the best, and I just wanted you to know that. Our train is moving into position. I'd like to thank everyone here for being with us today. It's a very pleasant occasion. Thank you.
And so we move on into the future, and new challenges still to come.
People who make the railway run, rolling on the rails of history, working together. Look how far